When you think about almost anything, there are ideas that we just don't pay much attention to. The one we're looking at today is like that. It's quietly shaping the universe, influencing everything from tiny particles to massive planets. It might even hold some big answers about time and life itself. It's the thing that pushes everything toward randomness, but still keeps a weird kind of balance, affecting simple things like reactions and big, complicated systems too. Here's something to think about. What does a hot cup of coffee have in common with the unseen forces that shape the universe? Most of us here are already familiar with the notions of entropy and the second law of thermodynamics. In fact, in contrast to other quantities such as mass or energy, it seems that entropy is a subjective quantity that depends on the macroscopic variables that an observer chooses to define or has access to. All physical phenomena, from atoms to galaxies, are governed by this basic principle. Yet the second law of thermodynamics seems to be a fundamental law driving our universe on the same level as the conservation of energy. During ideal processes, entropy remains constant, but in real-world processes, it increases. Thus, systems tend to become more entropic or more disorderly as they progress. An explanation for the unidirectional nature of time, also known as the arrow of time, is provided by this understanding. As you watch this video, entropy is all around you. Cells within your body are dying and degrading. The floor is getting dusty. The heat from your coffee is spreading out. Weeds overtake gardens and ancient ruins crumble. Zoom out a little and businesses are failing. Crimes and revolutions are occurring and relationships are ending. Zoom out a lot further and we see the entire universe marching towards a collapse. The inevitable trend is that things become less organized. The pull of entropy is relentless. Everything decays. Disorder always wins. Before you get depressed, there's good news. You can fight back against the pull of entropy. You can solve a scattered puzzle. You can pull the weeds out of your garden. You can clean a messy room. You can organize individuals into a cohesive team. But because the universe naturally slides toward disorder, you have to expend energy to create stability, structure, and simplicity. Successful relationships require care and attention. Successful houses require cleaning and maintenance. Successful teams require communication and collaboration. Without effort, things will decay. Let's use a deck of cards to explain. When the cards are neatly ordered, it's like having low entropy. But when you shuffle them over and over, they become disorganized, showing high entropy. This change indicates the passage of time. No matter how much you shuffle, the cards won't magically go back to their original order. This basic idea applies to many things we see in the universe. However, it leads to questions when we look at organized things like stars, planets, and life. To understand this, think of entropy not just as a disorder, but the number of ways you can arrange things without changing how they look or their energy. In our card example, each shuffle is a new arrangement, and entropy is all the possible shuffles. In simple terms, when we talk about increased entropy, we mean that systems tend to move from less likely arrangements to more likely ones. Ideally, a system's energy should be evenly spread, reaching a balance with its surroundings. This leads to a puzzling question. Why doesn't the entire universe already have maximum entropy? To answer this, we look at the universe's initial conditions. It's assumed that during the Big Bang, the universe started with very low entropy. While the past hypothesis doesn't explain why there's so little entropy, it suggests that the universe had to begin this way for it to evolve. The connection between the arrow of time and the second law of thermodynamics helps explain why time moves only forward. The idea is that, since our universe started with low entropy and systems tend to move towards higher entropy, all physical processes go from the past to the future. This perspective helps us understand why we see order in a universe that generally moves towards disorder. Living on Earth is crucial in this context. Earth isn't an isolated system. It receives concentrated, low-entropy energy from the Sun. This energy reduces local entropy, allowing life to thrive. Life processes, like growth and movement, generate order, but they also follow the second law of thermodynamics by increasing overall entropy through the dispersal of energy. Far from contradicting entropy, life embodies it. In fact, life is seen as a direct result of this law, pushing the universe towards maximum entropy. This understanding makes entropy not just an indicator of time, but also of life's presence and development. As we continue our exploration, we'll delve into more intriguing aspects of entropy, including its effects on cosmic phenomena, black holes, and the eventual fate of the universe. Entropy was originally introduced by Rudolf Clausius in the early 1850s in order to describe energy loss in irreversible processes, which turned out to be very useful in predicting the spontaneous evolution of systems like chemical reactions and phase transitions. Back then, understanding entropy was a bit like grappling with a vague math concept. There wasn't a clear way to explain what entropy really meant. Then, in 1877, Boltzmann, who laid the foundation for statistical thermodynamics, came up with a neat way to define entropy. Simply put, he said that entropy is a measure of how many different tiny arrangements, microstates, a system can have, while still matching the big picture conditions we observe, like temperature, pressure, and energy. In simpler terms, Boltzmann's entropy tells us about the hidden details of a system. When the number of possible microstates is higher, it means we have less knowledge about the true setup of the system. For instance, black holes in our universe have high entropy because we can only define their characteristics by their mass, charge, and spin. Since we only know these factors, there are many possible arrangements of matter inside the black hole that we can't pinpoint. The common belief about entropy is that it reflects disorder, stemming from the idea that systems we see as messy can have more possible arrangements than organized ones, resulting in higher entropy. However, this notion of order is subjective, leading to some counterintuitive examples that challenge the idea of entropy as a disorder. We often think of a crystal structure as more ordered than its fluid counterpart. Surprisingly, there are systems where the crystal form has higher entropy than the fluid phase under the same conditions, contradicting our usual intuition. For example, crystalline phases of densely packed tetrahedra. Despite our perception that uniformly distributed matter is disordered, it's actually unstable when gravity dominates interactions, Jean's instability. The most probable states with high entropy involve matter clumped together in massive objects, challenging the idea that disorder always corresponds to high entropy. A commonly stated version of the second law of thermodynamics is the entropy of a closed system can only increase. However, this isn't an accurate representation of the second law. A more precise statement would be, when a thermally isolated system transitions from one thermodynamic equilibrium state, A, to another, B, the increase in its thermodynamic entropy, S, is greater than or equal to zero. It's important to note that entropy lacks a well-defined meaning outside of thermodynamic equilibrium, a subject still actively debated among researchers. However, in scientific systems where we can continuously monitor a set of macroscopic variables over time, non-equilibrium entropy can be defined. Entropy in this context is based on the number of possible microscopic arrangements compatible with these macro variables. The second law naturally emerges from probabilistic reasoning, as seen in H theorem. Systems tend to spend most of their time in their most probable state, the one compatible with the highest number of possible microscopic arrangements. For example, in a simple system of light particles expanding in a box, the macro variables could be the number of particles in each grid of the box. The most probable configurations are those with evenly distributed particles, where each grid has the same number of particles. Grasping entropy involves contemplating the vastness of the universe. Observing the cosmic story unfold over billions of years helps us understand what entropy is. An interesting paradox arises when we consider the structured nature of the universe alongside the law of increasing entropy. Is entropy truly linked to disorder? If it is, how did the universe, with its stars, galaxies and clusters, manage to persist and evolve in an organized manner? An understanding of gravity, a force that tends to aggregate matter, is vital. The universe evolved because of gravity. Within the expanding chaos, it creates ordered regions by defying the law of increasing entropy. Stars, galaxies, and eventually life evolved in these regions of order, which contrasted with the dominant entropy. Therefore, another question arises. If gravity promotes order by bringing matter together, then why isn't the entire universe one massive mass with high entropy? In order to answer this question, we must go back to the beginning of time. The early universe was uniform, vastly different from its current state. This early plasma was hot, dense, and evenly spread, lacking the gravitational clumping observed in today's stars and galaxies. Back then, with no stars or galaxies, the universe was vast and homogeneous, exhibiting exceptionally low entropy. The past hypothesis suggests that entropy was at its lowest right after the Big Bang, and since then it has been on the rise. A puzzle remains: why did the universe start with such low entropy? Understanding gravity in this early universe with low entropy is crucial. Gravity played a key role in distributing matter uniformly after the Big Bang, a state of low entropy. The formation of celestial bodies like stars and galaxies became possible through gravity, converting potential energy into kinetic energy and then into heat, increasing entropy. Black holes, powerful gravitational entities, contribute significantly to entropy. Jacob Bekenstein and Stephen Hawking proposed that black holes contain immense entropy, adding to the overall entropy of the universe. The second law of thermodynamics is vital for the universe's existence and development. From the Big Bang to the creation of galaxies, planets, and life. Although the universe started with low entropy, it has since moved towards higher entropy, with gravity playing a crucial role in this progression. Understanding the intricate interplay between entropy, galaxy, and the universe helps us better comprehend our cosmic origins and speculate about the ultimate fate of the universe. Just as entropy is woven into our existence, so is time. We feel its influence in every moment, yet truly grasping it proves challenging. The arrow of time is a concept that describes how time constantly moves forward, never reversing. In line with the second law of thermodynamics, entropy follows a one-way trend, either increasing or staying constant, but never decreasing. Drawing from these parallel observations, scientists have suggested a potential link between entropy and the forward progression of time. The hypothesis is that the continuous growth of entropy over time is what imparts the unidirectional motion to time itself. The question might arise, why does time not move backward? The second law of thermodynamics provides a reasonable explanation. It is evident that the past must have had a lower entropy state than the future, given that entropy increases in forward flow. Time moving backward would violate the second law because entropy would decrease. Essentially, time is asymmetrical and intricately related to entropy. Time and entropy are related in more than just the direction they move. In addition to its implications for time, entropy's change rate affects time itself. As an example, we can take the cooling cup of coffee we mentioned earlier. A coffee's cooling rate, which corresponds to an increase in entropy, varies from moment to moment. The coffee cools down quickly when it is initially hot compared to its surroundings. As the temperature nears room temperature, the rate of cooling slows. Entropy increases at different rates. Time seems to pass more quickly when the coffee is hot and slower when it's cold. This means that the direction of time is not solely determined by entropy, but also influenced by our perception. Additionally, we can unravel the universe's evolution by studying the connection between entropy and time. According to the Big Bang theory, the universe originated from a highly organized and low entropy state. Some interpret this as the entropy of the universe continuously increasing over time, shaping the present universe. This idea is referred to as the past hypothesis. The past hypothesis provides a conceptual framework explaining the directional nature of time aligning with our everyday experiences and natural processes. However, it's considered an assumption about the early condition of the universe, and it is yet to be clarified why the early universe had such low entropy, posing a significant unsolved question in cosmology. Similarly, understanding the increase in entropy allows us to speculate about the future. The inevitable rise in entropy leads to the unsettling prospect of a heat death. At this point, the universe will reach maximum entropy, and its energy will be evenly spread throughout. This scenario means no more work can be done, ultimately bringing an end to time as we currently understand it. Despite this, we must emphasize that these conclusions are still speculative before drawing any apocalyptic conclusions. Scientific communities continue to debate subjects like the ongoing expansion of the universe and the absence of other influential factors, both of which are based on assumptions. The idea of entropy, which connects the physical processes inside our universe to the one-way and irreversible progression of time, plays a significant role in our exploration of time. We gain insight into our universe's possible future as we explore this connection, not only improving our understanding of the laws governing our universe. The connection between chaos and entropy is grounded in the behavior of dynamic systems, particularly within thermodynamics and chaos theory. Although originating from different fields, entropy from thermodynamics and chaos from mathematics and physics, these concepts share correlations, especially in understanding how systems evolve over time. Chaotic systems, known for their sensitivity to initial conditions, exhibit unpredictable and seemingly random behavior, contributing to increased entropy. In chaotic systems, trajectories in phase space representing all possible system states can explore a larger volume. This exploration leads to a rise in disorder and randomness, aligning with the thermodynamic concept of entropy. The irreversibility observed in chaotic systems, stemming from their sensitivity to initial conditions, mirrors the thermodynamic arrow of time, where entropy tends to increase over time, indicating a move towards greater disorder. The relationship between chaos and entropy emerges from the intricate dynamics of dynamic systems. The sensitivity to initial conditions and the resulting unpredictable trajectories contribute to an increase in disorder and randomness, highlighting the interconnected nature of chaos and entropy in the evolution of dynamic systems across various scientific disciplines. The world around us, from DNA to elementary particles, exhibits a discrete nature, making it more easily represented in digital form than analog. The life and career of physicist John Wheeler, transitioning from viewing everything as particles to fields and eventually information, reflects a progression towards understanding the universe as fundamentally informational. Edward Fredkin views the universe as a giant computer and emphasizes information as the essential constituent of everything. Information measured in bits is a fundamental unit describing uncertainty in a system. It is a measure of difference that generates a difference, indicating how much we don't know about a particular system, spanning from particle properties to black hole characteristics. In a mathematical theory of communication, Claude E. Shannon's work on measuring information quantity forms a foundational pillar of information theory, connecting energy, entropy, and information. Entropy, not disorder, measures the spontaneous dispersion of energy in a system. Events occurring spontaneously tend to distribute energy equally, increasing information. Shannon's insight allows us to associate entropy with information, suggesting that the universe evolves towards states of greater information content. What may appear as disorder to us is, in essence, information not yet understood, highlighting the evolving nature of our understanding of the universe. Most businesses face a high risk of failure, especially within the first 18 months, and an analogy to entropy helps explain this phenomenon. Entropy, a probabilistic concept, suggests that for every ordered state, there are far more disordered possibilities. Similarly, businesses tend to move towards disorder unless external energy is injected. Just as energy tends to disperse into a less useful state, businesses naturally drift towards disorder. Achieving and maintaining an ordered state, analogous to rearranging molecules, demands a continuous input of outside energy. The challenge lies in the fact that there are countless ways for things to go awry compared to the limited ways to make meaningful progress. While not a perfect analogy, it highlights the need for continuous effort to arrange and manage everything in a certain way for progress to occur. Self-organization can mitigate this need, especially with a strong goal, a capable team, and proper incentives. Entropy manifests in various aspects of a business, from employees forgetting training to equipment breakdowns and products becoming outdated. Successful businesses invest time and resources to minimize entropy through regular training, effective reporting, inspections, detailed records, and monitoring. Without these efforts, businesses are prone to chaos and potential bankruptcy. Unlike thermodynamic systems, businesses have the ability to reverse the impact of entropy. Striking a balance between creativity and control is crucial. Too much control can lead to disinterest among employees, while too little can result in poor decisions. Finding the right equilibrium is key to navigating the entropy challenge and ensuring a business's longevity and success. Life on Earth is influenced by the intricate dance of entropy. The Sun, our life-giving celestial companion, is the primary orchestrator of this dance. Contrary to common belief, Earth is not an isolated system, but is intricately connected to the broader universe. As sunlight continually penetrates Earth's atmosphere, it alters the dynamics of entropy. The Sun's energy, arriving as concentrated packets of order, holds the potential for life. This low-entropy energy is harnessed by plants through photosynthesis to produce sugars, fueling their growth and development. Animals, in turn, utilize this captured energy to sustain their bodily functions and enable movement. At each stage of this process, the energy disperses more widely, contributing to an increase in entropy. In this way, the dance of entropy, orchestrated by the Sun, plays a vital role in the vitality and functioning of life on Earth. As a matter of fact, life on Earth is highly skilled at increasing entropy. In the course of consuming food and respiring, organisms transform concentrated and useful energy into dispersed and less useful energy, thus increasing entropy. Solar power, for example, is a continuous source of concentrated energy that would incentivize the development of structures that disperse it efficiently. This could lead to the development of more effective energy dissipators in the future. The Sun maintains a low entropy level, which is crucial for life on Earth. After the Big Bang, the universe had low entropy, gradually transforming to its current high entropy state. This shift led to the creation of stars, planets, and life. Understanding the Sun's low entropy contribution and the universe's evolution helps us grasp our existence and cosmic development. Entropy weaves through the universe's history, starting with the Big Bang and shaping its destiny. Entropy, a guiding force, influences time by steadily increasing. The trend is expected to lead to a point called heat death, where the universe reaches maximum disorder. At this stage, energy is evenly distributed, and notable events become unlikely. One projected scenario envisions that, in the distant future, all usable energy will disperse, and even black holes, holding most of the universe's entropy, will release their mass energy through Hawking radiation, marking the end of time. Whenever entropy reaches its maximum, past and present become indistinguishable. No matter what direction time travels, the macroscopic universe remains the same. By eliminating entropy increases, the arrow of time would be eliminated essentially. According to the second law of thermodynamics, the universe tends to move towards its most probable state in the event of heat death. Interestingly, the same entropy that results in the heat death of the universe is also what provides the world with its beauty and complexity. As milk is poured into tea, intricate particles emerge between low and high entropy states that prevail in the middle of the entropy spectrum. It is the increasing entropy of our universe that enables stars, planets, galaxies, and even life to flourish. In this narrow range of complexity, it becomes evident that entropy is responsible for these things' existence. The importance of entropy becomes increasingly apparent as we conclude this video, as it impacts not only our daily lives, but also the very nature of the universe and our existence within it. An equilibrium embodied by entropy is paradoxical. While it is the antagonist of decay and deterioration, it also facilitates the emergence of this intricate complexity we observe in our world. An unmixed cup of tea or a blended cup of tea is simplistic and unremarkable in both extremely low and high entropy states. Between these two extremes, however, complexity and beauty flourish when the tea is stirred and the milk forms captivating patterns. Comparing the universe to a metaphor is fitting. Right after the Big Bang, the universe was highly uniform and had low entropy, hot, dense, and consistent. As time passed, it became less orderly, with stars, galaxies, planets, and life contributing to increasing entropy. Amid this growing chaos, there's a middle ground where life can exist, sustained by low entropy energy. This balance between order and chaos allows complex structures, like life, to thrive. Understanding entropy helps us make sense of everyday occurrences, from cooling coffee to melting ice. Beyond that, it addresses profound questions about life and the universe's origins, guiding us in predicting their ultimate fates. Studying entropy satisfies our innate curiosity about our existence and our place in the vastness of the universe. There are a lot of things in the universe that are awe-inspiring, even if they are brief. Continually exploring the secrets of the cosmos means that we must fully appreciate this middle realm of complexity made possible by entropy. We can marvel at the wonders of our existence, the splendor of our universe, and the intricate interplay between order and disorder that is entropy. We are able to better understand the cosmos when we understand entropy. Entropy will always increase on its own. The only way to make things orderly again is to add energy. Order requires effort. The pervasive occurrence of Murphy's Law in life, where things seem to go wrong more often than not, finds its explanation in entropy. Life's challenges aren't due to cosmic misalignment or external conspiracies, but are a consequence of entropy, the natural inclination towards disorder. It's a probabilistic law. There are more disordered states than ordered ones. The remarkable aspect is not that life has problems, but that we can overcome them. The quote, "Only the people sufficiently far out in the field get anything done," emphasizes that meaningful achievements require individuals who are willing to venture beyond the status quo, expending the necessary energy to create order amid the inherent chaos of entropy. And that's it for the video. Thanks for watching, and subscribe for more videos.